So last week we talked a little bit about some thoughts about the future of Casper, but the week before we did some applied type theory, in the sense that we looked at how we might implement some of the typing judgments in the OSLF paper that uses reflection to get some linear types. So I'd like to return to that discussion and apply it in real time to generating a type system for just the core of rholang. So let me do a screen share. So we'll begin here. This is only the minimal structure that is available. What in general will be available is, for every term constructor, there will be a corresponding type constructor. So these are just the built-in terms that we know must be there by our assumptions about how computation is structured. In the case of rho, we know that K will be par. We know that there'll be only one LK, RK gadget, which is the zero process. And then the constants will be all of the built-ins, right? So in rho, every constant string, every integer, every Boolean, those are all constants. So those will all be interpreted in this format here, or in this piece of the puzzle. But we will also have type constructors for all of the term constructors. So let's begin to write this down. So since we already have the term language, we can now write the type language. So I'll change everywhere on this page. I think I can do that here. Here we go. Okay, so you want P replace with T. And then Q will replace, Q will replace with U. Okay. And so that we can see that these are types and not terms, we will use the underline notation like we do in the paper. So that's kind of hard to see. So probably we should pick something else besides underline, but that's the notation that we picked in the paper. Well, it's useful to do this in real time. So then we can get rid of this stuff because that's not typing information. We might be able to prove some similar results. So that's our base level types. So we can compare that. So this piece here hopefully people can see what I'm pointing to, is going to be correspond to this piece here. And then for rholang, we will have types for each of the constants, which are effectively singleton types. So let me just stop there and say, does that make sense?
Yeah, this makes sense.
Okay. All right. Good. Good. So then the next thing that we've got is we'll have these types, right? So rather than introduce Greek symbols into our typing, let's just go ahead and make a big R and a little r. We also need, rather than to introduce these, we'll do star hash, let's see, ampersand and plus. So let's just do that now. So we'll have a type constructor. Let's call it G for gamma. If you give me a T, then so you see we'll do an R of T, an N of T, and so on. Okay. So we'll do this one as capital R, and T. So this part needs to be not, oops, I'll get rid of the braces. And then this one is not underlined. And for here, we'll do round brace N of T. And again, this is not underlined. All right, so then we're going to do the star, the ampersand, and the star, the hash, the ampersand, and the plus. So now we can do it this way. And this has to be like this. And it's unfortunate we can't do the same trick here that we can do here. Right. So we'd like to have a T and a U here. But these both must be supplied by here. So that's an interesting notational clash. Do you see what I'm saying?
Yeah, interesting.
Yeah. Since we're not, I'll just go ahead and fix that up. And the same here. Unfortunately, these are all parameters. So, okay. So we can now do that one. So instead of a star, we have a hash for par. and then we have an ampersand and a plus. Like that. Okay, so this is our base set of types, and then we have gamma, and then we can do the collections. All right, so now our collections are going to be sigma. So let's these are really finite sets. So
Can we just use curly braces? Like, does it make sense?
no, I mean, I'd like to in some way, but I think what I'll do is I'll do what Scala does. Okay, so let me just. So we'll just call this set. And then I think we want, there's a style of, I think we might be able to get it here. Nope. Yeah, that doesn't do it. Oops. Let me try something here. Well, I'll just I'll fix this up later. We'll just do it like that. Okay, so here we'll have a set called top. We'll have a set called empty. And go ahead.
I'm thinking we don't have this in Scala, right? On the type level, we don't have empty set.
That's correct. These two we don't have, but we do have the rest of them, right? Oh, sorry. There's also a set called unit. Okay, so those are, I think for, maybe that looks nicer. There we go. And now these we have, right? So yeah. Okay, so this we'll call and yeah, the reason, yeah, so this will be gamma of sigma. Yeah, there we go. So we have T cross T. This one will be underlined. and Tea Party. And then
I was expecting that you will write set instead of set of T, not just T, because on the paper you're using sigma, which is a set.
Correct. You're absolutely right. Yep.
So now I see it. This is like two sets.
So just for grins, this should be.
Oh, this is not set of T. Oh, yeah. This is set. So this set is not parametric in the element.
No.
How to think about this set?
You'll see in a second.
Okay.
Sorry, this one should be T. There. That incorporates T. So T comes from here. Whatever. I'll fix that in a minute. See, this is why going through these kinds of questions are precisely why this stuff isn't, why going through it like this is important. It's because these questions don't show up until you do this kind of exercise. And then,
yes.
And then, okay, and now this is going to be G of set. And since that's a type constructor, I'll leave it. Okay, so T sneaks in here. So we're essentially applying tupling. So if this is our tupling, and the reason we're calling it set, I suppose we could call it tuples, but if we call it tuples, it's going to be misleading. And the reason it's misleading is because we're always going to be able to weaken and permute, right? So we can permute the order of the tuples, and we can get rid of, not weaken, but contract. And we can contract extra elements in the tuple. So the fact that it's the witnesses appear to be tuples is they're not really tuples. They're really finite sets. So does that make sense?
Yes.
Okay. All right, cool. So then if we go here, so I won't do these. I'll do these. And well, yeah. Yeah. I think that's the way to do it. So these I'll leave as an exercise, but I'll do these. So then we want this one. And let me make this a little bigger so it's easier to see. Okay. So this is going to be morphism is too long. Let's just call it arrow. Okay, so arrow is going to be sigma arrow sigma and sigma arrow arrow and so on. So this will be set arrow set, and let's oops. There we go. And then this one is arrow. Oops. Come on, fingers. There we go. And then arrow, arrow set, and then arrow, arrow, arrow.
Arrow, arrow, arrow.
Oops. Oh, that was. And then finally, we close it out with G of arrow. Like that. And let's see, maybe we can make this bigger. Like that. I guess I can select all and then drop it down so everything fits on the page. And so you can now see how you do the linear ones. Oops, I've got an extra vertical bar here. You can see how we would do the other one, the linear arrow.
Yes, yes.
Okay, great. So now what we would then do is we would build our inference rules in terms of this typeset, or this collection of types. Right, so if we go back to overleaf, right, our inference rules, like this one, the tupling rule. So we'll have a judgment gamma that gives us that T1 is of type tau1, and likewise gamma also gives us that T2 is of type tau2. Then that allows us to conclude that from gamma alone, we can get the tuple of tau1, T1 and T2 is of type tau1 cross tau2.
And so, T1 and T2, this is like just a variable binding, or no. It's
this is an actual term. It's an actual term. So
yeah,
right. So our term language, we will now have to add. So our term language gets a little richer, right? So our term language goes. Let me move all this stuff down. Yeah, that's a good point. So the term language also includes
Type annotations.
Sorry, I guess I'll do it down here. Oh, no, I need to do it. So I'll move this like that. And then no, Isaac, it's not the type annotations, but we have to have, for example, T comma U, right? That's an instance of a tuple.
Yeah, like tuples. Yeah.
Right. And then we're also going to need, so if we look here, we're also going to need top empty unit, right? So these, sorry, not the types, but sorry, we don't need these. We might need a star for this one, right? But we do need the singleton. We'd need the singleton. We have the pars, but then we also need these these here. So we have to be able to, and you can see that from, oh no, yeah, these two. These are the ones that we need. So we introduce these as additional terms. So just to be super clear, so we have our tuples, and I apologize. It was my these should be P's and Q's. So I'll fix that later. But so we have R, and we did ampersand, and that's going to be T comma U. And then we also need R plus T comma U.
And how do we interpret these terms, R ampersand and R plus?
So thank you. I'm glad you asked. So let me just move these over.
Okay, yeah, that makes sense.
And do that. Okay. So in a language that's computationally complete, we can trampoline these away. We can say, well, we can implement these terms in terms of the stuff below. So in fact, all three of these can be implemented in terms of the stuff below. Right? We know how to do tuples in terms of this stuff. And we can just make a kind of tuple that is somehow syntactically distinguished. And we can make another kind of tuple that's somehow syntactically distinguished from this tuple. So these are really three tuples. And you weren't here at the last talk when I talked through this. But it has to do with how we think about the types and what it means in terms of probing. So if we go all the way back up here, what we're saying is the input to the type generation algorithm is a higher, as the higher order abstract theory. So you can think of it as a lambda theory. And what we insist the minimal structure is that it has to have a left and a right identity for K. So K is going to be a term constructor that is, without loss of generality, binary. So it takes two terms, one of which we can think of as program, the other of which we can think of as environment. So in the case of rho, the program and environment are completely symmetric, right? So you have a for comprehension and you have an output, and K is par, right? So program could be thought of as the thing that's waiting on the input, and environment can be thought of as the thing that's supplying the input.
Yeah.
And so the same thing will be for lambda. K will be application, a program will be abstraction, and our argument will be the environment. And then there needs to be either a left or a right, or if there's both, then they'll coincide. Identity for K, and then whatever built-in constants you have, and then there has to be a rewrite rule that goes from K of some terms to some function that uses the structure of the terms, the syntax of the terms. So that's what we're given, and we insist that your model of computation has at least this structure. So given that as input, we're going to change the theory. So first we add a term constructor R. Oh, so that means I also have to have that as a term. Glad I went over that. So we also have to have R as a term. Just for grins. It's not strictly necessary, but so R is saying we're applying gas to this term. It's resourced. We're giving it gas. Okay, and then this one and this one are related by the fact that now a K can come without gas. So you can have a K with gas, you can have an RK, or you can have just a K. If you have just a K, it's no longer able to rewrite. So the R is what we modify the rewrite rule so that if the R is present, then you can do the rewrite. And if the R is not present, you can't do the rewrite.
And in absence of R is like you've run out of gas or something, right?
Yeah, exactly.
Okay.
What that means is that K is now a datum. We've reified program back into data. So now we know that inside a K, we have a T and a U, and we'd like to be able to get them out. So the way we get them out is via cuts. So in particular, if I have an ampersand, if I have a par like this of two terms, then I can cut it with a tensor, and this will result in a parallel cutting. So I'll cut T3 with T1. Sorry, T3 with T1. So this is the R ampersand guy, or sorry, this is the R hash guy. So with an R hash guy, I'll cut a T3 with a T1, and I'll cut a T4 with the T2. And we can prove, it is sound to conclude, if you just run through all the definition, that is of type RK. because of the definition of the perp. So perp is up here in the abbreviations. Perp is to the RK. So this should probably be, I either need to fix that. Yeah, this should probably be squirrely braces RK, but that's the basic idea. You'll get to RK that way. And so this, with these notions, see, the reason these are abbreviations is it allows us to see that all of the different negations, and now we see that there are many negations. There's intuitionistic negation. There's a form of linear negation. There's this zeroing out style of negation. All of these things are programmable. You can, in fact, in general, make your negation, your dualizing object be other things. So you can have something over here that you are considering dualizing, and which goes along with the intuitions of Girard Quantal. So if you go look at a Girard Quantal, you'll see that the dualizing object is a parameter to his system. And that corresponds to the programmability of your different kinds of negation. And because of that, that then plugs into the cut rules down here. And then similarly, and this is where these terms here really can be Ks. So tensor is a K, but this one and this one, if I got that right, just make sure where we introduce, where the introduction of the, I just want to look for the introduction of the cup. Yeah, right. Cup and a tensor are just Ks. And then these guys are new terms. I think I've got that right. Just make sure I've got that right up here. It's up here. Yeah, there we go. So it's par and tensor. So I screwed up here. This should be star and plus. There we go. Oops. Okay, so star and plus. So that's where these two things come from. Is that these terms are used for probing these two kinds of term constructors are used for probing frozen Ks. Does that make sense? So a K without an R can be thought of as frozen. It's stuck until it gets to R, okay?
Yeah.
Since it's frozen, it's got some components in it, a T and a U.
Yeah.
I'd like to be able to go and get those. But in the spirit of Lambda, the only way to get them is to form Ks with them.
Okay.
Right. So for making a K is like a particle smashing, right? So this says when I smash two T's together, this is what comes out of the scattering.
Yeah.
Okay. So so a frozen K is like a bigger particle. It's got two particles inside it. And now and there are two ways I can smash. I can smash. I can take something that is a pair that's got another two pair particles, let's say T prime and U prime, and I can smash T prime with T and U prime with U. Or and that's this one here. Or this one says, go ahead and smash these two together and then smash T prime and TU together and then smash their results. So that's serial.
Yeah.
Okay, so that's what's going on here. So you either have a parallel smashing or serial smashing, and so that's what's happening here. So these are the terms. Let's see, is there a way to replace just on the page? Let's see if I can do that.
I just want to say, I think the Incredible Hulk would be very proud of this work.
Indeed, indeed. All right, let's take T. And replace it with P. And replace. Oh, okay. Well, it doesn't. I'll have to fix that later. We don't have enough time. I'll fix it later. But imagine that these are P's and Q's, not T's and U's. So these are the term languages, or this is the term language, right? And these are the types that are algorithmically generated. And then these are the inference rules that are algorithmically generated and can be used to check the terms that given terms have given types.
Can you write down one term when we have, for example, send? We can write some send and receive, and we can write the type for that, right?
Yeah, absolutely. So you know that for all the term constructors, you have a type constructor, right? So and so those rules I didn't bother to write down because that comes from that's more straightforward. But so let's do some basic type judgments. Okay, so we know that the term 0 is of type 0.
With the underscore, right?
That's what yeah. All right. And then we know let me get rid of all this. We know that if let's see. Suppose that gamma. Did I not put gamma in here? Seriously? Okay. Well, there we go. Okay. Now, suppose that gamma gives us, now I need a turnstile. Do I have a turnstile? Seriously? I'm not sure this will work. Oops.
Just do the vertical bar and the hyphen.
Yeah, fair enough. Yeah. Okay. Suppose that gamma gives us that Q is of type U. And also suppose that gamma gives us that, oops. Sorry about that. Suppose that gamma thinks that X is of type at I don't know, S. Okay.
Mhm.
Then we should be able to conclude that gamma thinks that X bang U Q is of type at S. Oops, let's do it this way. At S bang U underscore. Get rid of that. Like that.
I see.
That make sense?
Yes.
Oh, and I just wanted to make one comment. When you just say that 0 has type 0 underscore, this is in the empty environment, right? That's basically for free.
That's for free. Yeah. So in other words, I get to do the reality is oops that.
Mm-hmm. Yeah.
So hopefully that clarifies things. So this is how you so this is how you go from this theory, which is algorithmically generated, right? From what is it from? It's from whatever model of computation you supplied in a step-by-step fashion. We generate all the type structure. We generate all of the type rules, and we can apply that to each and every model of computation that has at least a program environment style reduction rule, which is basically everything, right? So the Java virtual machine has that,
Mm-hmm.
right? And JavaScript has that, and Scala has that, and Haskell has that, yada, 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 right? But in particular, rholang has that. And so we can apply it to Rho in the way that we've applied it. And obviously, all of this stuff here can be trampolined back into this part. We don't, and in fact, that's a general theorem. If the original computational model is Turing complete, then or functionally complete, then you can always trampoline this bit back into this bit. So this bit is entirely extraneous. So it's not like we're actually adding terms to the language.
Mm-hmm. Yeah, you can just build those terms out of what you already have.
You've already got exactly right.
Yeah. Interesting.
So that's an application of the OSLF to Rho.
Yeah.
Okay,
So,
can you just go back to the last canvas where what? Yes. Why did you put at the front?
Because this is a type constructor. This is a name, so the names have to have name types.
Oh, okay. So this is the constructor. Yeah, I was thinking that the bang is basically the constructor, but at is coming from the S. It's not part of the type of the last term, right? It's
Right.
part of X.
Yeah, that's correct. Yeah. So we have to give a type for X if we're going to form this term.
Yeah.
Okay.
Yeah. And so all of namespace logic is here, right? is inside this type system.
I wanted to ask how it compares with the behavioral types, but I mean, I know this is resourced, obviously, and that wasn't a feature in behavioral types, but
yeah, but you can get the one from the other, and that's the whole point of
Mhm.
that's the whole point of this definition here. This is actually modality.
Mhm.
So you can prove that the lollipop is modality, and so
Okay.
that's the other thing, is that you now get this relationship between linear logic and modal logic that hasn't been talked about in the literature as far as I know.
Mhm.
So what this does is it relates the session types, the Wadler style session types, to the Chi-race types. Yeah. So all of those things come together. So it's a fairly lovely, yeah, it's fairly nice theory, because the input is minimal, but it applies to an extremely wide range of phenomena, and in particular for our chain, it gives you, the ability to type your terms. Right, so you'll get a type inferencing or a type checking facility for free. Yeah, just and it lines up with the notion of gas, so you can use your types to check, do I have sufficient gas, these kinds of things. I mean, you have to be there. Some questions like sufficiency of gas will be extremely hard. They won't always terminate, but for a lot of things, you'll notice, oh, I don't have the gas to reach the state that I wanted to reach.
So we will be able to, for example, see some kind of loop, and with the type checking, we can see how many times we will loop and calculate the gas.
Again, some of those will not terminate.
Mhm.
Right. So anytime you're doing arithmetical stuff like that, you'll end up not terminating. Right. For basic stuff like, does this program reach what we're considering the dualizing state? Right. So you can think of it as a generalization of how system F guarantees termination for lambda. Right. So like all well-typed system F terms terminate. Right. So the generalization of that is whatever is your dualizing state. So that the type that represents the dualization, you'll always reach that dualizing state. So that's the programmable or generalized form of the system F property. Does that make sense?
Yes. This dualizing state, yeah.
Whatever you put to the right of the arrow that says, this is our notion of negation, right? That's going to give you, then the type system will guarantee that you reach that state.
I see. So this means if we have some if we are writing some function in lambda calculus, when we say that we have the base state,
there's some set of terms that you want to know that you reach. Right. That's what it'll do. Right. So instead of just like can't normalize anymore, what you do is you pull back from that. It's not that you can't normalize anymore, but you get to a term where you don't want to continue normalizing. You want to just hang out and wait and take and look at your stuff. right? So that's what would be the replacement of the negation in that setting.
I see.
Yeah. All right, got to go because we have developer stand up. Thank you all for your time. And I'm sorry. I have one other point. I realized in my in the exploration of the stochastic versions, the probabilistic versions of evolution, that I had not considered complex or negative probabilities. And so there's a variant of stochastic row where you use amplitudes, complex amplitudes instead of probability distributions, the way the stochastic pi calculus does. And so I've started to think about how to write that down, but that I think is also quite interesting because it's a much more robust theory of probability, right? Been tested a lot more. All right. Anyway, with that, I'll see you in developer stand up. Thanks.
Thanks.
Thank you.
Bye-bye.